I'm Sumati Hajela and I'm going to present the facts on fatty acids. Fatty acids, which occur in natural fats, are usually monocarboxylic and contain an even number of carbon atoms, as these are synthesized from 2 carbon units. These range from 4 to 30 carbon atoms and are straight chain derivatives. The chain may be saturated, containing no double bond, or unsaturated, containing one or more double bonds. Some fatty acids may have hydroxyl group or groups in the chain, and these are known as hydroxy acids, and still others may possess ring structure, which are known as cyclic fatty acids. They are generally present in esterified form as glycerides and phospholipids. If free, a carboxyl group of fatty acid will be ionized. Now, fatty acids differ from each other in length of hydrocarbon tail, degree of unsaturation, position of double bonds in chain, and short fatty acids like acetic acid, propionic acid, butyric acids. These are intermediates in metabolism. Second variety is the omega reference system, which indicates the number of carbons, the number of double bonds, and the position of the double bond closest to the omega carbon, counting from the omega carbon. This carbon is numbered 1 for this purpose. This system is useful in physiological considerations because of the important physiological differences between omega-3 and omega-6 fatty acids and the impossibility to interconvert them in the human body. This slide shows the use of Greek letters to designate carbon atoms. The carbon next to the carboxylic group is designated alpha, the next one is beta, and so forth. The most distant carbon is designated as omega. Sometimes carbon atoms close to the omega carbon are designated in relation to it. For example, the third from the end of omega is -3. This slide shows the summary of 4 common systems of nomenclature. First column shows the trivial names. Second column shows the IUPAC system names. Then the 2 columns show abbreviations. Out of them, first is carboxyl reference and second is omega reference. For example, palmitic acid is the trivial name, hexadecanoic acid is its IUPAC name. Then carboxyl reference system is 16:0 and omega reference is also 16:0. If we take the example of oleic acid, this is trivial name. In IUPAC, it is known as 9-octadecanoic acid. In carboxyl reference system, it will be known as 18:1 delta 9. In omega reference system, it is 18:1 in brackets omega -9 omega, with bracket closed. Likewise, linolenic acid and linoleic acid are also named accordingly. Fifth type of nomenclature is delta-X system. Here, each double bond is indicated by delta X, where the double bond is located on the 10th carbon-carbon bond, counting from the carboxylic end. Each double bond is preceded by a cis or trans prefix indicating the conformation of the molecule around the bond. For example, linoleic acid is designated as cis-delta 9, cis-delta 12 octa-decadienoic acid. This nomenclature has the advantage of being less verbose than systematic nomenclature, but is no more technically clear or descriptive. Lipid numbers. Lipid numbers take the form of C is to D, where C is the number of carbon atoms in the fatty acid and the D is the number of double bonds in the fatty acid. If more than one, the double bonds are assumed to be interrupted by CH2 units, that is, at intervals of 3 carbon atoms along the chain. This notation can be ambiguous as some different fatty acids can have the same numbers. Consequently, when ambiguity exists, this notation is usually paired with either delta X or N-X term. Fatty acids may be classified as saturated and unsaturated fatty acids. Saturated fatty acids contain no double bonds. Chain length is saturated. The molecular formula for a saturated fatty acid is CnH2n plus 1 COOH. For example, palmitic acid is C15H31 COOH. Other fatty acids like butyric acid contains 4 carbon atoms, caproic acid contains 6 carbon atoms, caprilic acid contains 8 carbon atoms, capric acid contains 10 carbon atoms, lauric acid is made up of 12 carbon atoms, myristic acid is made up of 14 carbon atoms, palmitic contains 16, stearic contains 18, arachidic acid contains 20, behnic acid contains 22, lignoceric acid contains 24, cerotic acid contains 26, montanic acid contains 28, and these are shown in next. This list shows common name, systematic name, structural formula and lipid numbers of few saturated fatty acids. For example, propionic acid. It is also known as propionic acid as systemic name. Its structural formula is CH2, CH3, CH2, COOH. Lipid number is C3 is to 0. Likewise, systematic name, structural formula and lipid numbers of butyric acid, valeric acid, caproic acid, caprilic acid, capric acid, lauric acid, myristic acid, palmitic acid, stearic acid and arachidic acid are shown in the figure. Classification of unsaturated fatty acids. Unsaturated fatty acids contain 1 to 6 double bonds in chain and degree of unsaturation depends on the number of double bonds present in it. These are subclassified on the basis of degree of unsaturation. Examples are monoethanoic acids or monounsaturated fatty acids. These are known as MUFAs also. These contain one double bond, for example, oleic acid and palmitoleic acid. Then polyunsaturated fatty acids are PUFAs. Their double bonds alternate with CH2 groups, which is a non-conjugated double bond system in polyenoic fatty acids and are usually of the cis type. These are divided as follows. A is diethanoic acid. This contains two double bonds. For example, linoleic acid. B is triethanoid ethanoic acid. This contains three double bonds, for example, linolenic acid and alloesteric acid. C is tetraethanoic acids. This contains four double bonds and example is arachidonic acid. Here is the list of some common unsaturated fatty acids. Their omega N number, common name, lipid numbers, delta N, structural formula, trans or cis form, and naturally occurring in or resources are shown in the table given in this slide. First example is omega 3 acid. Its common name is alpha linolenic acid. Lipid numbers are C18:3, delta N numbers delta 9, 12 and 15. Structural formula is given. It is of cis type and it occurs in flax seeds, chia seeds and walnuts. Likewise, other fatty acids are also shown in the figure. According to the nutritional classification of fatty acids, these may be non-essential and essential fatty acids. Essential fatty acids cannot be synthesized by the cell of the body and it must be obtained from other resources. Mammals lack the enzymes to introduce double bonds at carbon atoms beyond C9. Hence, all fatty acids containing a double bond at position beyond 9 have to be supplied in the diet. These are called essential fatty acids or EFA. Important essential fatty acids are linoleic acid, linolenic acid and arachidonic acid. Now the slides contain properties of fatty acids. The length and degree of unsaturation of the hydrocarbon chain determines many of the properties of fatty acids. Properties may be studied under following headings. First is solubility in water. Solubility in water decreases with increase in chain length and degree of unsaturation of the fatty acids. Short chain fatty acids are soluble in water owing to the polar nature of the carboxyl group, which ionizes at neutral pH. Higher fatty acids are insoluble in water but soluble in organic solvents. Except acetic acid, all other fatty acids are lighter than. This slide shows the table containing properties of fatty acids like their solubility in different solvents. First is water, which shows that if sample is immiscible in water, then oil or fat may be present. But if sample is miscible with water, then oil or fat is absent. If the solvent is alcohol and sample forms lower layer which dissolves on heating, oil or fat present. But if sample does not dissolve even on heating, fat or oil is absent. In chloroform, if the sample is miscible, oil or fat is present. If sample is immiscible, oil or fat is absent. Another property of fatty acids is their melting point or boiling point. Melting point and boiling points increase with increasing chain length but decrease drastically with increase in the number of double bonds. Fatty acids of chain length less than 8 carbon are liquid at room temperature. Saturated fatty acids 12 is to 0 to 24 is to 0 have a waxy consistency at room temperature, while unsaturated fatty acids of the same chain length are oily liquids. Fats containing fatty acids 18 is to 2 are liquid below 0 degrees centigrade. Saturated chains have an extended zigzag configuration at low temperatures but shorten at higher temperatures owing to rotation of C single bond C. This explains why biomembranes get thinner with increasing temperatures. Isomerism in fatty acids. The presence of double bonds in the fatty acid chain results in the existence of isomers. Cis isomers are common in nature but unstable, while trans isomers are less common but more stable. Most fatty acids in our body are of the cis type. Trans fatty acids are common in the triglycerides of dairy and meat products and in partially hydrogenated oils. Saturated fatty acids like stearic acid and unsaturated fatty acids with trans double bonds have linear shapes, but the presence of a cis double bond bends the shape of the molecule. Amphipathic nature of fatty acids. The carboxylic ends of the fatty acid molecules are hydrophilic and react with the cellular environment, while the R chains are hydrophobic and interact with each other. This amphipathic nature is important in the formation and function of micelles and membranes. Next property is of oxidation. Oxidation of the double bonds in unsaturated fatty acids yield hydroxy, aldehydic, and ketonic derivatives that undergo polymerization into resins. While this is a cause of rancidity in fats, oxidation of oils like linseed oil produces waterproof films. Halogenation. Halogenation of the double bonds is useful analytically. For example, the iodine number is the number of grams of iodine required to saturate 100 grams of a fat. Absorption of UV light by the double bonds is a basis for characterization of fats. Next property is formation of esters with alcohols. The esters of fatty acids with the trihydric alcohol, that is glycerol, are called neutral fats or triglycerides. Esters with some higher monohydroxy alcohols are called waxes. Formation of soaps with alkali. Fatty acids can make soaps with alkali. Sodium soaps are hard, potassium soaps are soft but costly. To make sodium soaps usable as toilet soaps, sodium carbonate or silicate is added in small amounts. This makes soap lather with even hard water. Soaps used for shaving are usually potassium soaps using coconut oil or palm oil as the source of fatty acids. To make a soap less alkaline and more smooth to the skin, excess of fatty acids are added. Zinc stearate is a soft powder which is non-irritant to the skin and water repellent, and it is commonly used for dusting powders. Calcium and magnesium soaps are insoluble in water and do not lather. Hard water which contains salts of calcium and magnesium is hence unsuitable for washing purposes. Fatty acids show properties of hydrolytic rancidity. and oxidative rancidity. Hydrolytic rancidity. On storage, fats become rancid. This is caused by the growth of lipase secreting microbes. Lipase splits fats into glycerol and fatty acids. Fatty acids impart unpleasant odor and flavor to the fat. Fat should not be mixed with water and kept in cold to avoid rancidity. Oxidative rancidity. Oils containing highly unsaturated fatty acids are spontaneously oxidized by atmospheric oxygen at ordinary temperatures. This auto-oxidation takes place slowly and forms short-chain fatty acids of C4 to C10 chain length and aldehydes, which give rancid taste and odor to the fats. This is observed more frequently in animal fats than in vegetable fats. Vegetable fats contain natural antioxidants which check auto-oxidation. Hydrogenation. Unsaturated fatty acids, either free or combined in lipids, react with gaseous hydrogen to yield the saturated fatty acids. The reaction is of great commercial importance since it permits transformation of inexpensive and unsaturated liquid vegetable fats into solid fats. The latter are used in the manufacture of candles, vegetable shortenings, and oleomargarine. Acrolein test. Fats, when heated in the presence of a dehydrating agent like sodium bisulfate or potassium bisulfate, produce an unsaturated aldehyde called acrolein from the glycerol moiety. Acrolein is easily recognized by its pungent odor and thus forms the basis of the test for the presence of glycerol in fat molecule. Fats are characterized or their purity may be checked or otherwise assessed by determining their chemical constants for individual fats. First is saponification number. Number of milligrams of KOH required to neutralize the free and combined fatty acids in a gram of a given fat is its saponification number. A high saponification number indicates that the fat is made up of low molecular weight fatty acids and vice versa. Iodine number. It is the number of grams of iodine required to saturate 100 grams of fat. Since iodine is taken up by the double bonds, a high iodine number indicates a high degree of unsaturation of the fatty acids of the fat. Acid number. Number of milligrams of KOH required to neutralize the free fatty acids in a gram of fat is known as acid number. The acid number indicates the degree of rancidity of the given fat. Richer missile number or RM number. The number of mLs of 0.1 normal alkali required to neutralize the volatile fatty acids contained in 5 grams of fat is the RM number. Polensky number. It is the number of milliliters of 0.1 normal KOH required to neutralize the insoluble fatty acids obtained from 5 grams of fat. Insoluble fatty acids are those which are not volatile with steam distillation. Acetyl number. It is the number of milligrams of KOH required to neutralize the acetic acid obtained by saponification of 1 gram of fat after it has been acetylated. It is seen that the treatment of fat or fatty acid mixture with acetic anhydride results in acetylation of all alcoholic OH groups. Thus, acetyl number is a measure of the number of OH groups in the fat. For example, the castor oil has high acetyl number 146 because it has high content of a hydroxy acid whose name is ricinoleic acid. This slide shows the references which are seen for writing these slides. Thank you.